Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about the compounding of steam turbines. So, before going to discuss this topic, let us first review the flow analysis through a nozzle. So, if we try to recall that basically nozzles and blades, these two parts together form the steam turbine. What is done in practice? Steam which is produced in the boiler, of course that steam is having high pressure, high temperature. That steam is allowed to flow through the nozzles, and while steam is passing through a nozzle, at the expense of pressure drop, the velocity of steam is increased, of course velocity of steam at the exit of the nozzle, and it is because of this increase in flow velocity of steam, the jets of steam which is coming out from the jets of steam coming out from nozzle increases, rather the velocity of steam jets increases, and that high velocity jets of steam impinge upon the turbine blades, and while that steam jets impinge upon the blades, there is a deflection of the steam jets because of the blade angle, and that jets suffer a loss of momentum, and that momentum is absorbed by the wheel of the turbine and it produces torque. So, you know that basically the flow nozzles and blades together form the steam turbine. So, before going to discuss about the compounding, why steam compounding is done, and then of course, we shall discuss about different types of compounding, but at least it would be important to know why this particular aspect is needed for the smooth and efficient operation of the turbine. So, let us consider a flow nozzle and this is the direction of steam flow and nozzle is insulated. So, we know that we have studied in thermodynamics, I have also discussed in the context of this course that if we apply steady state steady flow equation. So, let us assume this is the control volume, because we are going to apply first law for a flow process. Right. We have, so this is steam in and this is steam out. So, if we apply steady state steady flow equation, then we can write of course across this control volume. So, if we apply the steady state steady flow equation for the flow process across the control volume, then we can write the generic equation, that is q dot plus mi hi plus vi square by 2 plus gz I equal to me dot he plus v square by 2 plus gzd plus w dot. Since the process is steady state steady flow, so d is Cv dt equal to 0. Now, since we can see from this particular depiction that when there is a flow of steam through a nozzle, nozzle is insulated essentially to prevent any heat loss from the flowing stream to the ambience. So, this quantity equal to 0, and mind it, we have written this equation in the rate form. So, we have written this equation steady state steady flow in the rate form, and we are also not going to extract any work from the control volume. So, this quantity is also equal to 0, and we have discussed that this is the energy balance. So, this is the energy balance equation which is for the flow process, and energy balance is not a balance in an isolated manner, rather it has to be mass balance has to be coupled with the energy balance equation. So, basically if we apply mass balance, then we can write m dot I equal to m dot E equal to m dot. So, this is energy balance equation. Now, we can write from the steady state steady flow, we are assuming that this is exit. So, this is exit and this is inlet. So, cross sectional area of exit is much less than cross sectional area of inlet. What we can write from this is V E is much greater than V I. So, basically if that is the case, from this particular equation we can write that V E square equal to 2 into H I minus H E. Therefore, the exit velocity of steam V equal to 2 into H I minus H E. So, try to understand the velocity of steam at the exit of the nozzle is nothing but the total enthalpy drop across the flow nozzle. Next is, so if we express this enthalpy drop in kilojoule per kg, this velocity would be coming out 44.72 delta H power half meter per second. So, that is this, if we measure H I and H E in kilojoule per kg, the exit velocity of steam at the exit velocity of steam at the exit of the nozzle is 44.72 into del H power half. So, what we can understand is that in one nozzle, if we utilize one nozzle to have the pressure drop from boiler pressure to the condenser pressure. So, basically this is the we have studied in impulse turbine, there is no pressure drop when steam flows through the passage between the blades. So, the total pressure drop takes place inside the nozzle only. So, if we consider one stage, so consider a single stage turbine. Single stage turbine means what is stage? One row of nozzles follows one row of moving blades to form a stage of the turbine. So, stage is one row of nozzles, or these are fixed blades. Follows one row of blades or moving blades to form a stage of the turbine. So, turbine stage is, so if we consider one stage, so this is nozzle or fixed blades and this is only blade or moving blades. So, this is the first row of nozzles, this is first row of moving blades. These two rows together constitute to form a stage of a turbine, right. Now, when steam is entering into the flow nozzle, that steam is coming out from the turbine, from the boiler, and while passing through the nozzle it expands, that at the cost of the pressure drop velocity increases, and that steam while coming out from the turbine, steam jets strike the turbine blades, and after striking again steam is coming out from the first row of blades or moving blades, and it is because of this blade angle we can see that the jets suffer a loss of momentum, and that momentum is absorbed by the wheel of the turbine and it produces torque. So, if you would like to have the total pressure drop, that is boiler pressure. So, basically that steam which is coming out from the boiler now is entering into the row of or first row of moving fixed blades. So, this is P naught and V naught, and this is a so if this is the P and if this is the P, this is P1. So, we can understand at the exit of the nozzle pressure is P1, and theoretically there is no pressure drop when steam is passing through the passage between two consecutive blades in a first row or consecutive rows of moving blades. So, this is P1 and velocity is V1. Of course, velocity so this is P2 of course, and this is velocity V2, and this is P1 and velocity V1. So, P naught V naught is the pressure and velocity at the inlet of the nozzle, P1 V1, that is these two quantities are the pressure and velocity at the exit of the nozzle. So, the again pressure and velocity of steam at the inlet of the first row of moving blades is again P1 V1, and finally P2 V2 are the pressure and velocity of steam at the exit of the first row of moving blades. Now, this P2 equal to P1 and certainly V2 is less than V1, because a part of the kinetic energy would be absorbed by the first row of moving blades. So, now try to understand, if you would like to have the pressure drop from P0 to P1 or P2, and if you would like to have the total enthalpy drop in only once or single stage of turbine, then you know that the velocity that would be very high. So, this is the velocity of steam at the exit of the nozzle. So, try to understand the velocity of steam if we apply that same equation. So, if we are applying this equation between state 0 and 1, then of course, V1 is the velocity of steam at the exit of the nozzle according to the schematic. So, now this V1 is equal to 2 into H0 minus H1. This is the expression we have derived in the previous slide. So, what we can understand, if we design the turbine in such a way that the total enthalpy drop will be there in a single stage, then the velocity of steam or exit velocity of steam would be very high. Now, we have also expressed that this V1, right, which is very important, that V1 is equal to related, this V1 is directly related to the blade velocity. What is this? So, VB by V1 equal to cos alpha by 2. Therefore, VB equal to blade velocity equal to V1 cos alpha by 2. Alpha is the flow angle at the inlet. So, now if V1 increases, what we can see, this is the blade velocity will increase. So, that means if you would like to have total enthalpy drop in a single stage turbine, the speed at which the blades which are there in the first row, because it is a single stage turbine, will be having excessively high velocity. Now, question is, so that means when V1 is very high, which is obvious because we would like to have the total enthalpy drop in this first stage, then VB will be very high as well. So, now if VB is very high, let me discuss here. So, VB equal to that is pi dm n by 60. Dm is the mean diameter of the wheel, and n is the speed of the wheel. Okay. So, you understand that there are two possibilities to accommodate such a high VB. If we fix dm, so case 1, when dm is fixed, dm we cannot increase beyond a particular value to meet the space constraint requirement, because when you are installing turbine in a power plant, the turbine house we are also having space constraint. So, the dm cannot be increased beyond a particular value. So, if we keep dm fixed, then to accommodate high VB, n will be very high. That means the turbine will rotate with a very high velocity. If it is the case, then it has two consequences. What are those? First of all, number 1, such a high speed of the wheel will entail frictional losses. Number 2, if n is very high, then the centrifugal stresses will be very high. So, centrifugal stresses will be very high. So, these two are not desirable for the efficient or smooth operation of the turbine unit in a power plant. So, that means we can understand that allowing total enthalpy drop in a single stage turbine will lead to these problematic issues, and case 2 would be, so discuss about case 2. Case 2 would be, when n is kept fixed, then to accommodate such a very high VB, dm will be higher. Again, this is not a kind of desirable situation, as I said that increasing the wheel diameter beyond a particular value is not allowed, because we are having space limitation. The entire turbine unit which is there in a power plant, so we cannot go beyond a particular value to increase the diameter of the wheel. So, this is also not possible. So, what we can understand is that to have such a enthalpy drop, right, because try to understand, we would like to have drop of pressure from boiler pressure to the condenser pressure, because at the exit of the turbine steam pressure is the condenser pressure, back pressure. So, to basically if you would like to have it, then we have understood the problematic issues which are associated with this particular arrangement. We all know that a single stage impulse turbine is also known as D-level turbine, is having very high speed, and if the speed of the wheel is very if the speed of the wheel becomes very high, then we have discussed about the difficulties, and all these are not kind of desirable to of course for the smooth operation of the turbine unit. So, basically we have understood that two things. First of all, we want that, see, this V1 equal to under root 2 into H naught minus H1. So, we would like to have the total enthalpy drop is H naught minus H1. So, that means we can reduce V1. If we can reduce V1, then the problematic issues that we have discussed now will not be there, but to reduce V1, then we have to have very less enthalpy drop, but again it is not desirable. So, basically if we can if we can allow more enthalpy drop, more work output will be there, right. So, we are now trying to utilize the total enthalpy drop will remain same, at the same time not to encounter, not to invite all these difficulties or all these problematic issues. So, that means we need to design the unit in such a way that all these issues will be circumvented, but securing the total enthalpy drop will be the same, and that is what is done by the compounding of steam turbine. So, basically compounding of steam turbine is basically to utilize the total enthalpy drop. I mean, it is kind of an arrangement by which we can utilize the total enthalpy drop, but by eliminating all these problematic issues, and compounding of steam turbines is a way of kind of eliminating all these problematic issues, but at the same time we can utilize the total enthalpy drop. So, compounding of steam turbine is basically allows us to remove or circumvent the problematic issues but so by utilizing the total enthalpy drop same. So that means we are not going to compromise this enthalpy drop, but at the same time we can eliminate the problematic issues which are associated with high speed of the wheel as well as larger diameter of the wheel. So now this compounding there are two types of compounding, you know. One is pressure compounding or rotostaging. So basically compounding, or it is also known as staging, and second one is velocity compounding or Curtis staging. So now let us discuss about these two different types. So compounding is nothing but that if we consider that the enthalpy, total enthalpy is basically U plus PV. So internal energy of steam that we are not going to kind of disturb. So what we can do is that this enthalpy drop can be divided just by altering the drop in pressure inside the nozzle. So just by altering the drop of pressure inside the nozzle. So basically you can see that by changing pressure and velocity we can play with the enthalpy that will drop in a particular stage. So you know that U being a representative measure of temperature, we are going to, this internal energy will remain same, but only thing what we can do here is that by altering the pressure drop and change in velocity while steam is passing through the nozzle, we can have the change in H such that the total enthalpy drop will remain same, but we cannot have all these difficulties. So let us discuss about the pressure compounding first. So basically here we can have kind of pressure. So you know that enthalpy will drop. So if we look at the HS diagram. So this is state 0 and this is the total state. So if you would like to have so this is total state 1. So you can understand we would like to have this total enthalpy drop, but if we can have multiple stages and if we can compound if the total drop, so basically if it is compounded, if the pressure and velocity these two are compounded such that we can have the total enthalpy drop in a number of stages. So instead of having the total enthalpy drop in a given stage, if we can split that enthalpy drop equally among a number of stages, then we can have total utilization of the enthalpy drop, and at the same time we can eliminate the problem associated with this kind of high speed of the wheel as well as the larger diameter of the wheel. So, basically you know that this is the total enthalpy drop. If we can split it into say we would like to split it into a few stages. So, you can understand. So, this is 1 prime and this is 1 double prime. So, basically what we can write that this H naught minus H 1 prime equal to H 1 prime minus H 1 double prime equal to H 1 double prime minus H 1. So, that means if we have the enthalpy drop in a number of stages, so that the total enthalpy drop will remain same, is equal to H 1 H naught minus H 1. So, we can understand that enthalpy drop in a given stage, say H naught minus H 1 prime equal to H naught minus H 1 divided by 3. So, we are not going to have 3 different stages. This is the first stage. So, this is first stage, this is second stage, and this is third stage. So, basically we are having 3 different stages. Total enthalpy drop is H naught minus H 1, and that total enthalpy drop is now splitted among equal drop in a number of stages. So, basically what we can understand from this expression is that total number of stages is equal to delta H S total divided by delta H S stage. Delta H suffix S because this is isentropic enthalpy drop. So, delta H S total divided by delta H S stage is nothing but the number of stages. So, basically you can see that it is very important that number of stages which is needed, how many numbers, how many stages are needed to utilize the total enthalpy drop, but at the same time eliminating all these problematic issues can be calculated based from this. So, what we can understand from is that basically we would like to have enthalpy drop in a number of stages, and since we are we should utilize the total enthalpy drop, accordingly the total number of stages would be determined. So, for the pressure compounding, so you can understand we are splitting the total enthalpy drop into equally among a few stages. So, that means from this particular expression H is equal to U plus PV, we can understand that U, that is the internal energy, we cannot change because it is U being a representative measure of temperature. So, it is we are trying that the temperature definitely internal energy. So, basically what we can do from this particular definition is that we can change pressure and volume such that the enthalpy drop in a given stage can be altered. So, basically we can have compounding of pressure, and so we know that if you would like to have total enthalpy drop from 0 to 1, that is from boiler pressure to condenser pressure. Now, if the total pressure can be compounded in basically such that the total drop will remain same, but at the same time because of the drop in pressure in a nozzle, the velocity should not be very high. So, that means we are going to have the total drop in pressure in a number of stages instead of having instead of utilizing a given stage. So, basically pressure compounding is like this, that it corresponds to putting a number of simple impulse stages and total enthalpy drop is divided equally among the number of stages. That means, we will be having total pressure drop, but the pressure drop will be compounded such that the pressure drop in a given stage, and if we can be calculated, and if we can multiply the pressure drop in a given stage with the number of stages, that will be the total pressure drop, and that would be corresponding to total enthalpy drop. So, it corresponds to putting a number of impulse stages and stages. So, now let us look at how this particular configuration works. So, basically instead of, we know the total enthalpy drop. So, that is basically due to a change in pressure from boiler pressure to the condenser pressure. Now, if you would like to have total pressure drop in a single stage, that we have seen that velocity of steam at the exit of the nozzle will be very high, and to accommodate such a high velocity, either speed will be very high or diameter of the wheel will be very high. Now, instead if we can use a number of stages and the total enthalpy drop will be divided equally among the stages, in such a case we would be utilizing the total enthalpy drop, but at the same time the velocity of steam leaving one stage should not be very high, so that the speed of the wheel will be very high or the diameter requirement would be very high. So, if we try to draw it, the pressure compounding from the schematic depiction, it will help us to understand this particular arrangement in a more convenient way. So, this is blade or moving blade, first row of moving blade, and then this is basically nozzle or fixed blade. So, this is again nozzle or fixed blade, and finally we can have the So, this is again blade or moving blades. So, try to understand these two rows. This is the second stage and these two rows the first stage. Okay. So, now say velocity stream which is coming out from the boiler enters to this first row of nozzles or fixed blades, then it comes out from the first row of fixed blades or nozzle and strike the first row of blades, and then again it enters into the second row of fixed blades or nozzles, and finally it comes out from the second row of fixed blades or nozzle and strikes the second row of blades or moving blades, and then it comes out from the second stage. So, try to understand, we may have another stage, that is third stage, fourth stage, fifth stage, depending upon the requirement. So, the number of stages required, it is highly dependent on the total enthalpy drop. So, how many numbers, how many stages needed for a particular turbine unit, depend on the total enthalpy drop that will be there while steam is passing through the turbine unit. So, if we try to draw the pressure velocity diagram, so you know that what will happen, that the pressure which is, we are talking about pressure compounding. So, if we go back to the definition of enthalpy, H is equal to U plus PV, we are not going to have any alteration of U. So, what we are trying to do, we are trying to alter pressure and velocity in such a way that the total enthalpy can be, drop in enthalpy in a given stage can be altered, keeping in mind that the total enthalpy drop will remain same in all stages. I mean in all stages, such that the enthalpy drop in each stage will be equal and the total enthalpy drop in all stages will be equal to the enthalpy drop that we are going to have, that we need to have when steam is passing through the turbines. Now, so that pressure when, so basically when steam is passing through the nozzle or fixed blades, we know that at the expense of pressure drop, velocity will increase. So, the pressure will drop, and when steam is passing through the moving blades or blades, theoretically there is no pressure drop. So, that pressure will remain same. Again when the, so this is P naught, this is P1, this is P2, and again when it is passing through the second row of nozzle or fixed blade, pressure drop will be there, and then finally it will remain constant and it will come out from the second stage. So, this is P3 and this is P4. Now, at the cost of this pressure drop, velocity, say if this is the velocity, so this is the velocity of steam which is entering into the nozzle with V naught, that velocity will increase when steam is passing through the first row of nozzles. So, that velocity is this, and so this is V1. Try to understand. So, basically our sole purpose was to increase the velocity of steam which is now going into the first row of blades and moving blades. So, if we know the mass flow rate of steam, so that kinetic energy will be partly absorbed by the first row of moving blades. So, hence the velocity will drop. So, velocity will drop. So, velocity will drop here. So, this is V2, and again when the steam is passing through the second row of nozzles and fixed blade, then again velocity will increase because of this pressure drop. So, this velocity will again increase. So, this is the increase in velocity. So, this is V3, and finally, you know that when steam is that high velocity steam. So, basically again you can understand it is because of the compounding of pressure. So, we are going to have total pressure drop in a compounded manner, it is not in a drop in a given stage. So, it is because of this pressure drop further in the second stage of nozzle, second row of nozzles of fixed blades, velocity increases V2 to V3, and when that particular steam jet is again coming to or entering into the second row of blades and moving blades, kinetic energy will be absorbed by this row and velocity will drop, and finally velocity will go out. I mean the steam will come out from the second row of blades or moving blades. So, this is V4. So, this is V4. So, basically you can understand, had you allowed steam to expand only in the first row of nozzle, then the velocity would have been much more, and that velocity if we had tried to utilize in the first row of moving blades, then what we have discussed in the beginning of this class is that speed would have been much more, the requirement of diameter of the wheel would have been even larger. So, now instead of doing this, we are utilizing a number of stages, a few stages, and the drop in pressure is compounded in such a way that the total pressure drop is P naught minus P4 is remaining same, but the total pressure drop is now compounded in a number of stages, and hence the name pressure compounding is there. It is because of this pressure compounding you can understand that the drop increase in velocity even in the first increase in velocity of steam in the first row of fixed blades or nozzle is not very high, such that those problems will not be there. So, this is basically pressure compounding or rotor staging. Second is we shall be discussing about the velocity compounding or Curtis staging. So, try to understand, again velocity would be compounded. So, maybe what we can try, I mean it would be possible to have the total drop of pressure in a first row of nozzles, and then the rise or increase in kinetic energy, increase in velocity of steam, that would be very high and kinetic energy will be very high. So, instead of using the total kinetic energy in a single row, it would be again convenient, and we can also eliminate all this problem that if we can utilize that kinetic energy in a number of stages. So, that is we are now trying to utilize that high velocity of steam, but not in a single row of blades, but in a multiple rows of blades. That means, we are now trying to have compounding of velocity. So, velocity of steam that would be there at the end of the first row of nozzle, wherein we have utilized the total pressure drop. Such high velocity if we are trying to utilize in a first row of blades or moving blades, either speed would be very high or the requirement of diameter of the wheel would be very high. So, those are not again desirable. Instead of doing this, we can utilize the total kinetic energy that would be available at the exit of the nozzle in a multiple rows of moving blades. So, this is called compounding of the velocity. So, the high velocity of steam at the exit of the nozzle will not be utilized in a single row. Instead, that velocity would be utilized in a number of stages, so that we are compounding the velocity in such a way that the utilization of velocity or utilization of such a high velocity in a single stage will the problem associated with the utilization of high velocity in a single stage will not be there. So, let us draw the schematic again, which is very important. So, So, this is the nozzle and this is the steam flow. So, this is nozzle and this is first row of blades or moving blades, and this is first row of guide vanes, and this is second row of blades or moving blades. So, let me discuss here what is done. This is steam from boiler. So, steam from boiler is taken through this nozzle and this is the first row of nozzle wherein the steam is allowed to expand totally. So, the total pressure drop will take place in this nozzle only, and the velocity of steam that would be there is high velocity. A part of that velocity would be utilized in the first row of moving blades or blades, and the velocity which is coming out, velocity of steam or the steam which is coming out after doing some work on the first row of blades or moving blades is still having some velocity, and that velocity is again guided by the first row of guide vanes to direct to the second row of blades or moving blades. So, try to understand, it is the nozzle wherein total pressure drop occurs. It is because of this total pressure drop the velocity of steam leaving the nozzle will be very high, kinetic energy of steam will be very high. So, that kinetic energy is partly utilized in the first row of blades or moving blades, and remaining kinetic energy, that means the velocity of steam will be very high even at the exit of the first row of blades or moving blades. That steam is taken through the guide vanes, or that steam is allowed to pass through the first row of guide vanes, and that the sole purpose of these guide vanes, these are stationary. So, basically first row of guide vanes are stationary blades, and the sole purpose of the guide vanes is to direct that steam to the second row of blades and moving blades. Therein also a part of the kinetic energy will be utilized and it will rotate, and it will again go into the second row of guide vanes or stationary blades, and then again third row of moving blades or blades like this. So, try to understand. So, this is basically the nozzle and first row of moving blades. You know, I have discussed that nozzles are also known as fixed blades, stationary blades. So, the first nozzle and first row of blades and moving blades, this two rows form the first stage. The guide vanes, the row of the first row of guide vanes which is placed in between two rows of moving blades, and that means the first row of guide vanes and the second row of blades, these two forms the another stage. So, basically this is a two stage turbine. What we can understand, now let us draw the pressure velocity diagram. So, pressure of the steam which is coming out from the boiler and entering into the nozzle is very high, and the total pressure drop will occur inside the nozzle only, and the pressure will remain thereafter constant. So, this is P equal to constant. So, that is this is P1, this is P2 like this. So, at the expense of this total pressure drop, you know, velocity of the stream will increase. So, velocity of stream will increase, so this is V naught and this is V1. What I said, that a part of that velocity would be utilized, or part of that kinetic energy will be utilized in the first row of. So, that let me tell you that this is this would be in the first row only. So, basically I have to draw this again. So, if I now draw the so basically the steam pressure at the inlet to the nozzle is P naught, because this is the inlet. So, that is the boiler pressure, and pressure will drop drastically inside the nozzle, and pressure will remain thereafter constant as the steam passes through. So, pressure will remain constant thereafter. Now, if we try to draw the velocity, so basically this is the velocity of stream which is at the inlet of the nozzle, and that velocity will increase, and as I said that when that steam is entering into the first row of blades or moving blades, part of that velocity would be utilized. So, there will be again velocity drop, and while the steam is passing through the guide vanes or blades, there is again little drop in velocity, but I mean this is remaining more or less constant, and when steam is again entering into the rows of a second row of blades or moving blades, velocity will further drop. So, this is basically so this is V1, this is V2, and it is coming out. So, this is the two stage diagram we have drawn, and you can see that while steam is passing through the first row of guide vanes, so guide vanes are designed in such a way that there will not be any drop in velocity theoretically. So, you can understand that the total rise in velocity that is now partly utilized in the first law, remaining kinetic energy or velocity is utilized in the second law like this. So, that means that had we tried to utilize the total velocity only in the first row of blades, then the speed would have been much more, and also the requirement of wheel diameter would have been larger even. So, this is known as velocity compounding, as if the pressure is remaining constant, but we are trying to utilize the total velocity in a number of stages as if the velocity is compounded. So, what we can see that is that steam with high kinetic energy enters into the first row of moving blades or moving blades, that steam jets work on the first row of blades and moving blades, leaving the first row of blades and moving blades and enters into the first row of guide vanes. Therein there is no change in kinetic energy. Theoretically, that steam jets leave the first row of guide vanes and the steam jets enter into the second row of blades or moving blades, and again that steam jets work on the second row of moving blades, and so on. So, the process will that process will continue depending on the number of stages which is needed for the turbine unit. So, if we try to summarize that, today we have discussed about compounding, we have discussed about the why this particular arrangement is needed for the efficient operation of the steam turbine. Then we have discussed about the types of compounding, and then we have discussed both types, and we had seen how pressure and velocity compounding, these two compoundings work essentially for the efficient operation of the steam turbine unit. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.